recording and I'll share the screen. And let's start with an example of ANOVA. It'll be a nice little review for us. So there was a second example that we didn't talk about, I don't believe last week because we ran out of time. Rapid drainage of floodwater is crucial. Did we talk about this one, Jeannie?
I do not have it in my notes, but I
okay.
Have, again, I was like left.
Yeah, but you were here for the end of class and this would have been at the end. Okay, so rapid drainage of floodwater is crucial to prevent damage during heavy rains. Several designs for a drainage canal were considered for use in Atlanta. Each design was tested 4 times to determine how long it took to drain the water in the reservoir. Can you conclude that there is a difference in the mean drainage times for the different channel designs, and use A or alpha equals 0.01? So again, the thing about ANOVA, to help you recognize that it's ANOVA, because that's going to be one of your challenges as you head into the final exam, is recognizing that you need to use ANOVA, is that one, you have quantitative data that has been sorted into categories by some variable. In this case, our variable was the channel type, and they have those numbered, but those numbers are simply labels. We had designs 1, 2, 3, 4, and 5. So again, just as a little nice review for us today, and I apologize for my confusion, but ANOVA we use whenever you have quantitative data sorted, so left out a word, quantitative data sorted by a qualitative variable. Okay, so again, you've got numbers, the drainage time, sorted by the design or the channel design. That's one clue. The fact that we want to do ANOVA as opposed to Kruskal Wallis, which we're going to talk about in a minute, is that this one is talking about the mean. Again, typically when we're examining the mean, we are doing a parametric test, and the parametric test is the ANOVA. The hypothesis testing process hasn't changed. And oftentimes, one of the things, you can't just rely on the fact, well, oh, I have a table of information to recognize it as ANOVA. But oftentimes, the information that you need for ANOVA, because you have them sorted into groups, is often displayed in a table. So one clue, not the defining clue, but one clue that you're going to do ANOVA is that you have a table of information. Again, that's not the only defining factor. But the first step, as we've talked about numerous times in any hypothesis test, is to state the hypotheses. For ANOVA, the null hypothesis will always imply equal, and the alternative will imply not equal. We also talked about there's a couple of ways to state the hypotheses. You can use the words or you can use symbols. And it's really kind of a preference of the researcher, or maybe depending upon your audience. And so if I look at this statement towards the end, it says, can you conclude that there is a difference in the mean drainage times for the different channel canals? Okay, so we see that word difference. Again, I hope the word difference helps you to realize that that means or implies they're not the same. And mathematically, that would be represented by the symbol not equal, which means that statement is the alternative. And honestly, we could use that statement as our alternative hypothesis. We could literally say there is a difference in the mean drainage times for the different channel designs. And that's perfectly acceptable. We know that the alternative, or excuse me, the null in this case is going to be the exact opposite. And we would say there is no difference in the mean drainage times for the different channel designs. And using that in the sentence form is okay. Again, the idea that there's no difference implies equal. The fact that there is a difference implies that they're not equal. Now, the words are perfectly acceptable. I'm completely fine with that. Some people prefer symbols. And what we're comparing is the mean or the average, excuse me, for each group. So we could write the mean of channel 1 is equal to the mean of channel 2 is equal to the mean of channel 3 is equal to the mean of channel 4 is equal to the mean of channel 5. Now, I don't know what that mean is. I don't know what that average value is, but I'm trying to say that they're all equal to one another. And so you can just write out that string of equal statements. In the alternative form, we would say at. Some books use the phrase at least one. Some use the phrase at least two of the means differ. Because if one's not the same, then really there's a second one that's not the same. So different books, different strokes for different folks. Again, I'm perfectly fine if you want to use the sentence, and usually that sentence you can copy verbatim from the problem. Step 2 in the process is to identify the information that you need. And again, for analysis of variance, that information is typically presented in table form. Notice that this information runs horizontally, that the drainage times for channel 1 are on the first row, channel 2 are on the second row. So make sure you're reading the table or the display correctly. The other thing that we need is alpha, and the last sentence tells us to use alpha equals 0.01. If our significance level is 1.01, that means our confidence level is 99%. Okay, so we have that information. Step 3, same as always, is to calculate the test statistic. We're calculating an ANOVA, which is actually an F test statistic, and its p-value. And we talked about what all goes into that calculation, I believe, last week. So if you were not here for that class, you may want to go back to catch some of that detail. Now, guys, remember, we don't do this by hand. We use Minitab to do it. So I'm going out to Minitab, and we need to put in our data, because to do any kind of analysis, you have to have data. There's two ways you can enter the data here. I much prefer to put each individual category or group, in this case, each channel design, in its own column. You can put all of them in a column and then code it, if you will. I'll show you in case you prefer that. I prefer to put them in all in different columns, but we could put the drainage times all in a single column and then code it with its channel. So I would have, for example, 41.4 corresponds to channel 1, and 43.4 is again channel 1. And so I would go down through there and indicate side by side. Again, I prefer to do it, excuse me, I've got the yawns, in individual columns. So under channel 1, I'm going to type the 4 times that we were given for channel 1. For channel 2, I'll put it in its own column. You want to be extra careful, as always, to make sure you don't mistype something. Whoops, I mistyped that one. The fact that it's added a 0 at the end doesn't affect the values itself. It just thinks it's 2 digits because of my typing error. Okay, so I've entered the data from the table. Now notice again, even though the table presented the values horizontally in rows, when you enter it into Minitab, you have to put it in columns. You have to convert it to a column. Okay, going vertically rather than horizontally. Remember also that we can run 2 case tests at the same time that we're calculating our initial test statistic. And so we go ahead and do that. So we go to Stat, ANOVA. We're doing one way. I have my response data in separate columns for each level. Okay, I put them in individual columns. So I have to choose all of them. I have channel 1, channel 2, channel 3, channel 4, and channel 5. You choose all of them. We go to options. We're using a 99% confidence level. We always choose two-sided. For 2 case tests, we click on the button that says comparisons and select 2K. Everything else stays the same. I just click the box next to 2K and I click OK. And I click OK again. Now remember, we get lots and lots of information here. We need initially the table or the information labeled analysis of variance. I'm going to copy it. Okay, from this table that we get in Minitab, what we need is the F test statistic, the F value, and the corresponding P value. Okay, so we would write those down. My F test statistic is 9.24. My corresponding P value is 0.001. We write those down. Then we go to step 4. Step 4 is the same as always. We're going to make a decision about whether we should reject or fail to reject the null by comparing the p-value from Minitab to the level of significance that's given in the problem. So my p-value from Minitab is 0.001. My level of significance is 0.01. Again, we compare those digit for digit. The first number after the decimal is 0 for both. Second number, I have 0 for the p-value, 1 for the level of significance. 0 is less than 1, so the p-value is less than or equal to the level of significance. When p is less than or equal to the level of significance, we reject the null. Step 5, as always, is to write the conclusion. Now again, let's go back up to our hypotheses and think about what this means. We have rejected the null. If we reject the null, that means the null is false or invalid. And by default, then, that means that the alternative is true or valid, which means there is a difference. And so my conclusion can basically be, again, that same statement, but we need to include the level of significance. So if we say at the 0.01 level of significance, there is a difference in the mean drainage times, go back up here, make sure I get it, times for the different channel designs, for the different channel designs. Now, again, what ANOVA tells us in this case is that there is a difference in how quickly or how slowly those different designs drain the floodwater. It does not tell us which one or ones are different. That's why we use the post hoc test. The post hoc test gives us more insight into which one or ones is or are different. The post hoc test that we use, which we actually already ran, is two-case test. Okay, so let's go back over here to our Minitab results. And if I keep scrolling, one of the things you can look at, not that you have to, but you can look at the actual means. Notice that channel 1, channel 2, and channel 5 all seem to have a mean around 44. But channel 3 takes 30.9, takes about 31 minutes to drain the flood water, and channel 4 takes only about 29 minutes to drain the flood water. Okay, so you can look at the values of the mean. So looking at those values, it looks like 3 and 4 are different. If I keep looking here, okay, it says means that do not share a letter are significantly different, meaning 3 and 4 are significantly different from 1, 2, and 5. If you look at this grouping method, what you're encouraged to look at is this probability plot or probability graph, and I'm going to copy it over to my paper so we can talk about it. Okay, if you go back to the PowerPoint and look at the instruction, let's see, did I close that PowerPoint down? Yep. On 2 case tests, it says if the confidence interval range doesn't include 0, the difference between these means is statistically significant. So if we're looking at this probability plot, and hopefully you can see it, but the 0 line is in green. So when you compare, this one compares channel 3 to channel 1, this one to channel 4 and 1, 3 and 2, 4 and 2, 5 and 3, 5 and 4. So all of these, again, thinking about what doesn't include 0, are those 1, 2, 3, 6 different options, which all of those have either channel 3 or channel 4. So we would conclude that channel 3 and channel 4, okay, channel 3 or channel 4, we probably could use an and there as well, are statistically different from channels 1, 2, and 5. And again, if I go back and look at those mean values, okay, if you go back and look at these mean values, it appears that channel 3 and 4 drain faster than 1, 2, and 5.
So with this, we have to think about when we are reaching the conclusion, like those 2 channels could be worse than the other 3. Like they could have,
yes.
like if they were a higher mean. So we need to both look at the statistically at the significance, but also like in which way they fall on that mean scale to see if they're like better, like those 2 could potentially be statistically different, but also worse than the other 3, right?
Yeah,
okay.
Right. Yeah. And like if I were the engineer that's maybe trying to decide which channel design I would want to use, based on this, we know that there's a difference in the channel designs. If let's say if we had concluded that there was no difference, then it wouldn't matter which design I picked. But because there was a difference, I want to try to figure out maybe which one is the best option. So running 2 case tests, I can see that 3 and 4 are statistically different. But then I want to also, like you say, go that step further to say, well, are channel 3 and 4 the better option, or would they, in a sense, be the worst option? And again, that determination I get from looking at the means. And I can see that the mean or the average time it takes for 3 and 4 to drain is approximately 14 minutes faster. Okay, all the others are close to 44. 3 and 4 are around 30. So they're taking only 30 minutes to drain. And the faster the water drains, the less likely you are to have flooding, which is a good thing. Or less likely to have flooding. Yes, I said that right. So, you know, if I'm the engineer, I'm going to probably start looking at channel 3 and channel 4. I might do more research to figure out which design we want to go with. And sometimes that further research might be, well, does one cost more than the other to, you know, to create or to install? Usually answering one question leads to another question.
So like kind of going back to our two, like I'm thinking back to the, I'm thinking about the mini project 4, going back to the TNT test. I remember and we do the post hoc test with that to decide whether it is large, you know, small, medium, large. But we need to go back to the means to kind of determine, okay, which one is, you know, maybe better or like, and make a determination there similarly to this. Is that correct?
Yeah.
Okay.
Yeah. With a 2 main T test, you're looking at like you're comparing just one to the other. So you can even start out saying, you know, I know you're doing the education one. So you might say, you know, the scores for the percentage that were proficient at Rome City is less than the percentage that are proficient in Floyd County.
Right.
So
okay.
you've already made that. You are starting out at the beginning in your hypothesis saying, yeah, I think there's a difference, and I think it's less. I think one is less than the other.
Gotcha. In the ANOVA, like you could actually break it down further and go like the different, more different variables. Like
you could look at individual schools then.
Right.
You could start, if you looked at Floyd County, you could look at, and I don't know a lot of the names of them, but you could look at like at Armurchie High School, or, you know, Armurchie Elementary School compared to Alto Elementary School compared to I don't know what another school is over there,
West
but
End. West End.
West End Elementary.
So you could do this. That would be the ANOVA. Like,
yes, that would be the ANOVA when you get it, when you break it down. ANOVA, you have to have 3 or more groups. So I know there's more than 3 elementary schools in Floyd County. I don't know about Rome City.
There are more than 3 in Rome City.
There are? Okay, I didn't know that. Okay, so that's the parametric test. That's if we have numbers, again, sorted into categories. It's the same hypothesis testing process, but the post hoc just takes us that one step further. ANOVA lets us decide, yes, there is a difference, or no, there's not a difference. And then 2Ks begins to let us see which one is different. But sometimes, as we've talked about in the past, you can have non-parametric, or you have a distribution that is not symmetric or not normal. And when that is the case, we can still make that comparison of 3 or more groups. But again, we begin to look at the medians instead of the means. That's what makes it a non-parametric test, is that our data is not normally distributed. We may not even know what kind of distribution we have. And so we compare the medians instead of the means. And that non-parametric test is called Kruskal Wallis, or the H test. So we're going to talk about that for just a minute. Again, it is comparable to the one-way ANOVA, but it's less powerful, again, because we don't have the assumption that our distributions are normally distributed, or that there are any kind of particular distribution. And we don't have to assume that we have equal variances. If you'll remember, when we did the Minitab command, we had the little box checked that said assume equal variances, which is one of the assumptions we make for analysis of variance that we would have talked about last week. Again, we take all of the data from 3 or more populations as a group. Instead of looking at them in individual categories, we put them all into a group and we rank them. This value is first, this value is second, this is third, fourth, fifth. We rank them. And that rank actually becomes the data, the numbers that we use to calculate our H-test statistic, which approximates the variance, the differences within those ranks. Okay, so it's a little bit different. It's very similar to the Wilcoxon signed rank, where the data again is ranked based on where it is in the list. The H-test statistic has a distribution that can be approximated by the chi-square distribution, which we haven't talked about yet. So I think I have some information there for you. But in order to use the chi-square distribution as the approximation for the H, you have to have at least 5 values for each population. So if you've got 3 populations, you got to have 5 for the first population, 5 for the second, and 5 for the third in order to use the chi-square. And I believe I put some information here on about chi-square. The chi-square distribution is similar to the F distribution that we talked about for ANOVA. It is not symmetric. Okay, so you no longer have that guarantee that you have that nice bell-shaped curve with the mean in the middle, and that's a mirror image of each side. The chi-square distribution is actually skewed to the right. You have a lot of values on the low end and very few. The mean is going to be just to the right of your peak. And because it is right skewed as opposed to symmetric, the values for the chi-square, or in this case the H, will always be equal to 0 or be positive. You'll never have a negative H-test statistic. The chi-square distribution is different based on the number of categories or groups that you have. The display that I have here has a degree of freedom of 4, which means I would have had 5 groups, because the degrees of freedom is the number of groups you have minus 1. When you have approximately a degree of freedom of 90, when your degrees of freedom is greater than 90, your chi-square distribution begins to be approximately normal. Remember, we've talked about how that the normal distribution can be used to approximate a lot of the other distributions at a certain point. And the certain point where chi-square begins to be approximated by the normal is when the degrees of freedom is 90 or higher. Okay, so that's the chi-square distribution. We're going to talk more about chi-square in Module 4, but I introduced it here because that's the distribution that supports the H-test statistic for Kruskal Wallis. Oh, and it's hung up. When you leave it on there too long, it gets hung up. So let me have to exit out of it and then go back into it. Okay, so there are still, as there is with many of the tests that we do, there are still some assumptions that we make about Kruskal Wallis. One is that our dependent variable, okay, so your Y, your output, is measured at the ordinal or the continuous level, meaning it's either at interval or ratio. But typically it's going to be at the ordinal level, that idea of being ranked. Your independent variable consists of 3 or more categorical independent groups. Again, there's an independence in the observations. There's no relationship between the observations of each group or between the groups themselves. What occurs for one group doesn't affect the second group, doesn't affect the third group. There's no, crossover there. The distribution of scores for each group of the independent variable have the same shape, meaning that we're kind of assuming they have the same variability that when we start. Again, for our purposes, we're going to use Kruskal Wallis if the distribution is not normal. Okay, we're kind of keeping it as simple as we can. So if it's normal, we're going to use one-way ANOVA, which is really the better option because that test is more powerful because you're relying on the means. But if it is not normal, we're going to run Kruskal Wallis. The other thing about Kruskal Wallis is you never, ever run 2Ks with Kruskal Wallis. Okay, you never run 2Ks with Kruskal Wallis. So our hypotheses are very similar to what we had with the one-way ANOVA, but instead of addressing the mean, we are addressing the medians. So we can say the medians of the groups are the same. There's no difference in the median amount of the variable. For the null, again, null is going to be equal and the alternative will be not equal. So again, but we're addressing the medians instead of the means. So here's our process. We ideally would like to determine if the populations are normally distributed or not. You will likely be told that in this scenario. If you were doing this in the real world, you could run the normality test. You could run Anderson-Darling. But if you have a normal distribution, we're going to run the one-way ANOVA with 2Ks. If it's not normal, we're going to use Kruskal Wallis. And to try to decide, again, we could look at the box plots or the descriptive statistics if we needed to, or we could run Anderson-Darling. Okay, so then we will, if we decide we need to use Kruskal Wallis, we're going to do Kruskal Wallis. The steps in the hypothesis test are the same that we've been using throughout. It's just a matter of which test statistic we calculate. And in this case, it would be the H test statistic. So I have the information on the screen for Minitab. One of the differences with Kruskal Wallis, Kruskal Wallis wants you to put all of the response values in a single column and then to code it with which group it's in the adjacent column. Okay, whereas I was putting individual doing channel 1, channel 2, channel 3, channel 5 in its own column. Okay, for Kruskal Wallis, we have to put the quantitative variable in a column, all of them in the same column, and put the group they're in the adjacent column. And I'll show that to you. This slide walks you through how to create. If you want to look at the box plot or the descriptive statistics, it walks you through how to do that. For Kruskal Wallis, which is a non-parametric test, the response variable is always the quantitative, the number, and the factor is your qualitative. How are you sorting? Okay, so we're going to take a look at some examples and look at how to do this. Okay, so on the same printout that you had for ANOVA, you should have two examples for Kruskal Wallis. Okay, I need to print my data, so let me have Minitab, my computer, print this for me real quick, so I can have the data to look at. Okay, so while my printer is printing, let's see, it says a meteorologist wishes to see if there is a difference in the number of deaths in the United States due to severe weather events. The data from the past 6 years are shown here. At a 0.05 level of significance, is there a difference in the number of deaths from the different weather conditions? Okay, so if you look at this table, you have information about deaths related to lightning, tornadoes, flash flood, or a blizzard. Okay, and so we want to conduct a hypothesis test. Now, it doesn't tell us here that it's not normal. So we're going to go the extra step and do the and look at the box plots at least to make that determination. So let's go over to Minitab, and I'm going to get a new page so we don't get confused. And again, I didn't readily recognize it as being Kruskal Wallis. So ideally, what would happen on a test is you would be told that, you know, it's not normal or it's an unknown distribution. At this point, I could say, well, I don't know what kind of distribution we have. It didn't tell me. So that might be my default go-to, that I'm going to run Kruskal Wallis. But I really should check, because if it's normal, I could reuse the ANOVA. Okay, but thinking that because I don't know what distribution it is, it didn't tell me, I don't know, so I'm going to use Kruskal Wallis. I'm going to enter my data, but here's what I have to do. I have the data, I have 24 data values. I have 6 for lightning, 6 for tornado, 6 for flash flood, and 6 for blizzard. Okay, so I'm going to put in column 1, I have to put all of the numbers. So I'm going to put the number of deaths in column 1. Next to it, I'm going to put kind of the coding system and put the weather. So for example, if I put in the lightning, so I have 39, 41, 73, 74, 67, 68. And then I'm going to go back, and I know that this was lightning. So I'm going to put lightning in the column next to it, so that I know that those 6 values okay, and then I'm going to move on to the next one. So the next 6, again, I'm going back under column 1 under number of deaths, starting at row 7. I'm going to put in the ones for tornado: 30, 39, 39 again, 53, 50, and 32. Whoops. Okay, so I know that those 6 were related to a tornado. So I go back in column 2, and next to those 6 numbers, I'm typing the word tornado so that when I'm finished, I'm only going to have 2 columns of data. Okay, so then I go back and I'm on the 3rd column, and which is flash flood. Okay. If you wanted to create some kind of, code here, you could, you might use FF for flash flood, T for tornado. I'm typing the words out. And then I'm going back to column 1 again, and I'm going to enter that 4th column. And what's going to happen behind the scenes is Minitab is going to look at all of these numbers and rank them. It's going to say, okay, this value is the lowest, so it's first. This one is next. It's going to rank them. Okay, this is blizzard. All right, so again, what I've done is I've put all 24 data values in a single column. And next to it, in the adjacent column, we've indicated what the weather event was. Are you understanding how you have to enter the data this way? Because if you don't, it doesn't work. Okay, again, I want to kind of investigate whether or not it's normal or not. So I'm going to look at the box plots, and I want to look at them all at the same time. And this is on the PowerPoint, but I'm going to do it. Graph, box plot. We have them sorted with categorical variables. So I'm doing multiple Y's with categorical variables. So my Y variable is the number of deaths. My categorical values, which are the words, and I want, just leave that way. Options. Okay, that's okay. Okay, so I choose the number of deaths, which is my Y. I'm sorting by the weather events, and I'm going to click OK. And what I get, let me copy this so you can see it. What we get is this box plot. Okay, the first one shows the blizzard. The second one shows flash flood, lightning, and then tornado. They're in alphabetical order. Okay, but notice, for at least flash flood, the box itself is towards the low end, and you have this long whisker. So that's not, remember, the box is supposed to kind of be in the center. Blizzard maybe kind of looks normal. Lightning is definitely not, because look how your median is way up there. Okay, so none of these really look to be a normal distribution, except maybe blizzard. If you're still not convinced, okay, we can also look at the descriptive statistics. I can have it calculate the descriptive statistics, and we only really need the mean and the median for each one. We could look at mode, but mean and median's enough. Okay, if you compare, remember, okay, see blizzard, the median and the mean are virtually the same. So we would think that's normal. The mean is is bigger than the median. So that's got some kind of skewness going on. Same thing with lightning. And we could argue that tornado is approximately normal. So they're not all the same. They're not all normal. So we cannot do a one-way ANOVA. We're going to have to do Kruskal Wallis. Y'all following me? If not, speak up. Okay. So we have to do Kruskal Wallis because the distributions are not normal. Again, ideally that we hopefully would tell us that in the problem, but it didn't. But if I assume that they're not normal, then we run Kruskal Wallis. So we go to our first step in any hypothesis test. Okay. The first step in any hypothesis test is to state the hypotheses. Even with Kruskal Wallis, the null will imply equal, the alternative will imply not equal. And so if I go back up here to my problem and read it again, let's see. It says, is there a difference in the number of deaths from the different weather conditions? Notice, excuse me, in this problem that it says, is there a difference? It doesn't have the word mean in it either. So that could be another clue that it's Kruskal Wallis, that it doesn't talk about the means. So again, I see the word difference. Difference, again, would imply that they're not equal. So this statement is the alternative. So we really could use this same statement with the addition of one word. We could say, there is a difference in the median number of deaths caused by severe weather. Okay. The question just says there is a difference. Okay. We add that word median because again, we are testing the medians. Again, there is a difference implies that it is not equal. So our null, which is the exact opposite, would be there is no difference in the median number, excuse me, of deaths caused by severe weather. Now we kind of already know there is a difference because we looked at the medians, but the question is it statistically significant? Step 2 is to identify the information, which we've actually already done because the information was presented in table form. So this is step 2, is to identify the players. And we're told to use alpha equals 0.05. So if we have a 5% level of significance, that means our confidence level is 95%. Again, we've already decided we're going to do Kruskal Wallis because the distributions were not normal. So step 3 is to calculate the test statistic, which in this case is going to be the H, and its p-value. And again, we do that with Minitab. But again, as I mentioned, when you do that in Minitab, you have to put the data in as I did earlier. You put all of the quantitative data in column 1, and you put the corresponding category that it's paired with or is under in the adjacent column. Okay, so here we go. Stat. We're doing a non-parametric test. So we go to non-parametrics. We choose Kruskal Wallis. The response is your quantitative variable, which would be the number of deaths. The factor is the categories, which is weather. I click OK. And my results appear up top. Okay, it does give me the descriptive statistics, figures the median for each group. It gives me the average or the mean rank. Okay, so it gives me some information, but what I need is this value under the test. The values under the test. Let me get it pasted. Okay, notice that it gives you one value for not adjusted for ties, and then the second one adjusted for ties. Guys, we use not adjusted for ties. Okay, we will use not adjusted for ties. That means if you had a value that had that's the same number, so it's tied for a rank value, there is an adjustment that can be made. We're going to use the not adjusted. So again, we have our H test statistic is 5.54. The corresponding p-value is 0.136. Minitab did the work. It ranked the data and then calculated the H test statistic. Then we move to step 4, which is the same as always. We're going to make a decision. We compare the p-value to the level of significance. So our p-value was 0.136. The level of significance is 0.05. Making a comparison, first digit after the decimal, 1 compared to 0. 1 is greater than 0, so P is greater than the level of significance. So we would fail to reject the null. And then lastly, we would write a conclusion like we always do. Now, go back and think about what this means in the context of this problem. If we fail to reject the null, we fail to reject the null. That means that the null is true or valid, and the alternative is false or invalid. So based on the evidence we have, there is no difference in the median number of deaths caused by severe weather or the different weather conditions. Okay, so we would write at the 0.05 level of significance. there is no difference in the median number of deaths. I'm gonna go back up here and pick up the same sentence. Deaths from the different weather conditions. Okay, so there's your conclusion. Again, guys, we haven't changed the process that we're using. What's changing is which test we're running, which affects our test statistic. And again, we used Kruskal Wallis here because one, they didn't tell us that the distributions were normal. And so if we make that we make the assumption that they're not, Kruskal Wallis is my best option. We did investigate and found that they are not, at least two of them are not normal. So we had to resort to Kruskal Wallis. Questions?
I just have a general question. I know, like, okay, so I know that if the example we had, the deaths, like we had 50 in each one, is that, I know when we get enough that we can do the central limit theorem, is that something we can apply to that so that we can actually do analysis of variance, or am I misunderstanding kind of, do you know what I mean? Like, am I able
Yeah,
to?
I think that I'm not sure that we can apply the central limit theorem because, again, the assumption is that you would have a normal distribution, which I realize the central limit theorem would force it to be normal. But then the other assumption that we're making if we run one-way ANOVA is that we have the equal variances.
Okay.
And so even if you run central limit theorem and force it to be normal, we may not have the equal variances.
Okay.
Other questions? Okay, so Thursday, I'm gonna get it right. Thursday, we will actually begin module 4 and talk about a correlation and regression. Okay, I'm working on those PowerPoints now and I'll get them posted up. Okay, but you have quiz 9, which will be due on Sunday. You have mini project 4 over 1 mean or 2 mean t-test that is due on Monday.
And we should have all the notes and everything for quiz 9, so we should be able to go ahead and do.
Yes, you should have those now because quiz 9 covers ANOVA and Kruskal Wallis and 2Ks.
Okay, thanks.
So you're good on that one. Okay, ladies, I will see you guys on Thursday then. Have a good afternoon.
You as well. Thanks.